All right, party people, it's Thanksgiving week, so I don't have assignments for you, but I'd love it if you would walk through dinosaurs through time with me today. So, part of the funny thing is I see a poster like this, which is for children, and it should get them excited about dinosaurs, but some little part of me that has probably died says those dinosaurs didn't live at the same time, which is fine. Art and whimsy are wonderful, and getting people excited about science is wonderful. But today I want to walk you through just a couple of the mechanics of why we understand certain dinosaurs lived through time and separate from each other. Here's another example. I actually had this this puzzle for my child, and it just killed me putting it together. Those animals didn't live at the same time. Let's explore. Now, something I've provided for you in this course is this timeline of dinosaur life as a tree of life sort of superimposed on a timeline which we've been using in this class. But I want to talk about how we put something like this together as, a body of scientists. So we talked quite a bit about plate tectonics, and you chose a plate and worked on it. So what I want to do now is kind of bring that to fruition by saying, well, what does that get us? So let's consider through time that we can start, and all these illustrations are by Ron Blakey, who was a professor at Northern Arizona University. So if we step through time from today and we try to picture what the globe looked like as we step back in time, the Cretaceous, the Jurassic, the Triassic, and before that, okay? So let's go the other way. Once upon a time, we have conceived of Pangaea coming together as a supercontinent. Now, it's not as crisp and clear as it looks in children's books. It's actually a lot of pieces, but that's okay. Pangaea is together during the Triassic when dinosaurs appear on this Earth. Pangaea starts splitting apart at the end of the Triassic, giving us a Jurassic world which is a bit more fragmented, and ultimately a Cretaceous world that is very fragmented as these continents continue to separate from each other. One of the things I want to bring to your attention is this big body of water flooding across what will become North America as we step forward through time. Now these are some continents you can recognize, and this is how we see Earth today. All right. Now, this is something that I'm just presenting to you in a vacuum. In this course, we are not getting into how these processes unfold, just that there is a lot of solid observation work underpinning this. And this is then things we can take from geophysicists and say, okay, so you say that's what the continents were doing. Interesting. That then allows us as paleontologists to think fairly dynamically. So here are a bunch of paleontology students out looking at some rocks, which you can see are dipping at a funny angle. They're tilted. That probably wasn't the way they were originally deposited. These rocks were probably originally deposited horizontally and laterally continuously. The rocks that these students are looking at, let me minimize myself to make sure that this shows, what we are actually looking at here are rocks representing the latest Triassic depositions in this region of Earth and the earliest Jurassic depositions in this region of Earth. And there is a lot that we can do to put that together. So for example, these are rocks, we were just in Dinosaur National Monument in that picture. And in these illustrations, what they're showing you is that you can consider a pile of rocks that you witness in one place, compare it to a pile of rocks you see in another place, and then on a different part of the monument in a different area, and you can try to connect the layers in all of these rocks based on which fossils are found there, which environments are represented, and what the sediments are like. A lot of this work is done with things that are not flashy and not exciting. We work a lot with dinosaurs in this class, and that's fun. These are fossils of pollen, the stuff that gives you sinus trouble in the spring. Well, those things can make extraordinarily good fossils that help you correlate these layers back and forth. But I'm not going to cover them much in this class because, oi, all right? But it allows us to do a few things. We can correlate from spot to spot. We can connect rocks that should have formed at the same time. And much more importantly, we can try to figure out what the environments were like. So here is one of Ron Blakey's reconstructions of just Utah. What did Utah and neighboring states, here's Utah, neighboring states, what did Utah look like through time? Well, if we start in the Miocene, which is part of the Cenozoic, so around when whales were evolving in the oceans, then we can step back in time and we can think about when there was more salty lakes, there were more salty lakes here. And then if we go back into the Cretaceous, remember I pointed out there was a big flooding of our continent during the Cretaceous. And if we step backwards through the Mesozoic to the Jurassic, we have these tremendously large bodies of sand. They're called ergs, and they basically are like oceans made out of sand that leave behind sand dune rocks, which are pretty cool. Finally, the Triassic, stepping back even further in time, the Triassic was pretty lush around these parts. And the Paleozoic, we actually had a lot of ocean water and ocean animals here. So if we revisit, now we're these same people looking from this trail in Dinosaur National Monument, these rocks that show us those transitions can help us look at rocks that represent this lush, green rivers and plants setting to this dry, arid desert and sand dunes and kind of arid sea setting. And we can go to those exact rocks that represent these different habitats. So that's how on a small or regional scale we can reconstruct habitats, and we can figure out the environments that the animals were living in, and also we can rank the environments as to how they fit in time. Now, what I want to consider here for a moment is all of the fossils we might talk about. So paleontologists gather data from all over the world, and we have this project that's been going on for the last 40 years or so, where we compile our observations of fossils into this big database. I can go to that database, any of us can go to that database and say, okay, well, I want to see dinosaur fossils from North America from the Cretaceous period. Hey, that's a whole lot of dinosaur fossils from North America from the Cretaceous period. And this is the latitude and longitude roughly of where those fossils were published as being found. Then I could also say, let's consider Jurassic fossils. Okay, well, North America doesn't have as many Jurassic dinosaur fossils. That's okay. How about the Triassic? Okay, well, fewer Triassic dinosaur fossils. All right. Paleozoic. Well, then you're a bit out of luck, aren't you? Because dinosaurs weren't around in the Paleozoic. Dinosaurs begin in the Triassic. So now the problem becomes, if you're a person who wants to study dinosaurs, but you want to know about where they were and what their habitats were and how the continents were arranged, you can't reconstruct all that using dinosaurs because they just don't give you a squat to work with. So what paleontologists typically do, I showed you those pollen fossils earlier, but another kind of fossil that we use that I love are ammonites. Ammonite fossils are from extinct squid-like animals that had a seashell. And those seashells, my goodness gracious, did they make useful fossils. They're just everywhere. Every continent. You can find them in Antarctica, the shores of England, you can find them in Sri Lanka. Anywhere you go, you can find ammonites, pretty much. And they are around for the last 500 million years, them and their kin, other cephalopods. And so we can use these very odd looking seashells, which we collect in these museums, to try to figure out, okay, now where am I in time and space and habitat? So if we go back to that same database, and instead of looking at dinosaurs, we say, well, where are the ammonites through time? Many more to work with. Now we're looking at cephalopods, which is ammonites and squids and nautilus, all that good stuff. Let's look at them in the Cretaceous. That's a lot of them. Notice how there are a lot of them in the middle of North America during the Cretaceous? Might have to do with that flooding seaway. Lots of them in the Jurassic. Lots of them in the Triassic. And the Paleozoic, we have a lot too. Here's just the Permian period, because ammonoids and cephalopods were around for a really long time before dinosaurs. It's also way easier to find their fossils. Let's play the same game, but we're going to look at this database and what it has for cephalopod fossils on the whole planet. Okay, Permian, Triassic, Jurassic, Cretaceous. Pretty cool, huh? Also, what's neat is you can see that these things are usually kind of around the edges of the continents. Is that because a long time ago, these continents were not in these positions? These are sea animal fossils we're looking at, remember. So this is all the way to the Cenozoic. Now let's step back in time, but let's look at these fossil collections with the continents in the positions they belong. All right, Cenozoic, that's since most of the dinosaurs petered out, but we still have plenty of cephalopods. Cretaceous, Jurassic, Triassic, Permian, which is the end of the Paleozoic. So now we're looking at that Pangea splitting up through time thing, and we can put Pangea together, all right? So when we show these maps of the continents, and when we show different fossils and animals living during these different periods, I just want you to get the gist that this is an enormous body of work that has taken people around the world 200 years to even get started, and we're always refining it. We discussed also absolute dates recently, which we're not discussing more in depth today, but they're definitely a part of refining this picture in terms of the periods that we actually decide. All right, so that's sort of the basics of paleobiogeography, and the idea that we can distinguish when and where animals actually lived, so we can try to figure out who lived together. Now, I want to get back to this idea of all of these animals did not live at the same time. That's silly. But, you know, even though we know that intellectually, what I want you guys to do is feel deeply in your heart when you look at a certain kind of dinosaur and say, I know who he was friends with, right? Know that there were different times that dinosaurs lived together. So here, I like this picture very much because it brings the point home. I see here a Tyrannosaurus Rex in this lovely shade of puke green over here. And I see this very beautiful rainbow Stegosaurus. Did those two animals live at the same time? They did not. In fact, a Tyrannosaurus Rex died, like the last Tyrannosaurus Rex that ever died on Earth was a lot closer in time to your birthday than how close that Tyrannosaurus Rex was to the last stegosaur that ever lived.